Okay, the purpose of this tutorial is to build on our HEC-RAS model and show how to change some of the features so that we can start to increase our flexibility. And the three basic things we're going to learn to do here is to add different flow rates into the same steady flow analysis. So analyze multiple water surface profiles. Then we're going to change the boundary condition and see how that impacts our water surface profile. And then we're going to look at how to create more complex geometry so we can start to move towards maybe more realistic channel geometries. Okay, so starting with we're going to start by adding more flow rates to our analysis. So we're still working with example 5.2 in the text, and we're going to use the new geometry that we created in the last tutorial that performed better. Okay, if we want to analyze multiple water surface profiles, or multiple flow rates essentially, we can go to our steady flow analysis tool, and we can open new flow data. So we can create new flow data. Okay, we have flow 1, now we're going to have, let's call this flow 2, and okay. Let's increase the number of profiles. So instead of analyzing one flow, let's analyze 3. So when we enter 3 and apply the data, we now have profile 1, profile 2, and profile 3. And this might be if you were analyzing, say, different return event. You might analyze a 2-year flow, a 10-year flow, and a 25-year flow, something like that. So I just picked some values that will work. Let's analyze 15 cubic meters per second. Then what we did last time are 30 cubic meters per second, and then let's double it to 60 cubic meters per second. Apply the data. And we still need to set our reach boundary condition. So this is the same flow. We're still going to have critical at the downstream end. So we go to downstream, and we'll use the same boundary condition critical. Click on that and click OK, and we're good to go. Now we apply the boundary condition. Again, we have no locations of flow change. The last thing we need to do is save that flow data to, save it, and we can exit. Okay, and since the geometry is already prepared, again, this modular setup of HEC-RAS allows us to combine different flows and geometries. We're ready to go to running our steady flow simulation. We're going to create a new plan. So, new plan. We'll call this plan 3. We can use the short identifier P3 and click OK. Now, when you start getting all these plans, it's useful to use the plan description. So let's say analysis of 3 flows, 15, 30, 60 cubic meters per second. So we can keep track of what all of these. And again, we'll use geometry 2, the updated geometry, and now we're going to use our new flow data, flow 2. And again, we expect it to be subcritical based on our qualitative analysis. And so we can save our plan and go ahead and run our simulation. So let's do that. Let's compute. And again, everything is good. We got to the solution, and we've now got our answer. We can close. Sometimes I recommend, especially after you get a solution, it's a good time to save your project. So let's go ahead and save. And now we can start to look at our results. So I'm going to open the profile. Again, I like to look at the profiles first, view profiles. And you say, let's make this larger. Look at this and you say, wait a second, we're only seeing one profile, but we did all those calculations. What happened? So we need to go to options, and we need to select all the profiles. So go to profiles, and you can see 2 and 3 are here. They're just not selected. So we can add 2, and we can add 3, or it's easier, we'll just do select all, and you get them all over there, and then hit OK. And now you see we've got profile 1, which was 15 cubic meters per second, then 30, and then 60. These plots can get a little bit dense, as you can see from the legend. So maybe in this case, we might want to select variables. We may no longer want to show the energy grade line. We may want to take that critical depth elevation out. We may want to leave it in, but let's take it out. And you see it's a little bit easier to see now. So here's our profile 1, profile 2, and profile 3. So we've analyzed 3 different steady flows in a single computation. And so we could rename these instead of profile 1, 2, and 3. We could say maybe this is the 10-year event, this is the 25, and this is the 50, something like that. Okay, we can close this. And then you can analyze the data exactly as we have done before. You can look at individual cross sections, right? They've left the water surface elevation off. We could add it back with variables if we want to see that energy grade line. But again, it gets a little bit more dense. And we can, again, click through all of our profiles. So there's 0, our downstream boundary, 10, 20, et cetera, et cetera. We can, and you can analyze exactly as we did the previous solution. Okay, 3D cross sections. This looks kind of cool, right? You get your full 3D. Now, one thing that you might notice here is look at our bank stations. We've now got this water surface elevation way up here. What's going on here? So let's go back to our cross sections because these can help us answer those questions. Let's go to the upstream boundary, the river station 1400, and look at this. Here's our bank station, but we have a flow all the way up here. What's happened is the flow has exceeded our channel and it would be spilling over to the floodplains. We did not provide any floodplain geometry. HEC-RAS simply assumes these are vertical lines and continues the calculation. So this is not, I would not trust this water surface elevation. If I see this in my simulation, I would say, okay, I need to go back to my geometry. I need to add floodplain data to my cross section. I'm not going to do that here, but we could go and refine the model further if we would like to do that. But let's not worry about that. We'll keep our flows in the channel. But if you see this, you need to extend. This would tell me either the channel needs to be deeper to accommodate that flow, or I need to add the floodplain geometry so I can see how the floodplains are inundated for this larger flow. Okay, so just keep in mind that problem can happen, and you need to deal with it accordingly. We can look at the summary tables the same. This is plan 3. You can select your different. So this shows the data for the 3 different profiles. If you'd like, you can always, similar to what we did before, you can only look at one profile or look at them individually. And the detailed cross section. Here's it's kind of nice. You can select from your 3 profiles and you can see. And so notice here we get a warning when we go to profile 3, which was our 60 cubic meters per second, which exceeded the bounds of the channel. The cross-section endpoints had to be extended vertically for the computed water surface profile. So you have a problem here. Same with 1300, 1200. So this is a large flow that's exceeding our channel. Okay, so that's how you analyze multiple flow rates at one time. Very handy tool. That you will use a lot. In fact, oftentimes you will not analyze only a single discharge. Okay, the next thing we'd like to do is change the boundary conditions. So let's take our, let's go back to our initial channel here. And let's say, excuse me, one more thing I have to do so I can update this. Oh, sorry, my computer seems to be running a little bit slow. Let's see how this works. Okay, you know what? I'm going to cut this off. Oh, you know what? We're going to keep going. Looks like we're okay here. Okay, and so let's take this the channel geometry and let's change the boundary condition. So previously we had our water surface a free overfall. Let's change that from a free overfall. Let's say it's a known water surface elevation in our reservoir. So here's our reservoir. And let's say we now have a known water surface elevation above our, so this will be a known water surface elevation. And let's set it equal to 1.8 meters so it stays within our 2-meter channel. So 1.8 meters above this. Remember, this was elevation of 0. And so this will be our elevation of the water surface in the reservoir. is 1.8 meters. Okay, so that's going to change our flow. Remember, our normal depth line is now going to be down here. So instead of an M2, we now expect an M1, which we've also dealt with in class. Okay, so let's go ahead and see how we would do this in HEC-RAS. Okay, again, geometry stays the same, right? Even though the channel geometry is still trapezoidal, still the same slope, we can go to our steady flow data and just update that. And we want to create new flow data. So let's call this flow 3. Okay. Let's do just a single cross section, and actually, or sorry, single flow rate, and we'll use our original flow of 30 cubic meters per second. Now our boundary condition has changed. We now, at the downstream end, we have a known water surface elevation. So we can click on that, and we can enter our known water surface elevation is 1.8. All right, again, it's got to be relative. That's why setting that 0 at the beginning is so critical. So we're 1.8 meters above that. We click OK. And then OK to accept it, and then apply the boundary condition data, and then save our flow data, and we're good to go. Okay, so it's fairly straightforward to change boundary conditions, and known water surface elevation is quite common, especially if your flow is entering a reservoir where the elevation is monitored. Okay, so we can exit the flow data. And again, this modular format allows us to just put that together with our geometry in a new plan. So we go to run our steady flow simulation, and we want a new plan. And oops, P3, let's go ahead and call this plan 4. Click OK. Our short identifier P4. Our plan description, we could say 30 cubic meters per second with known surface elevation in a reservoir. Something like that, so that we know what it is. We're going to run same geometry. Now we're going to run our new flow that we just created, flow 3. Again, we know from our geometry that this is going to produce a subcritical flow. So we leave this at subcritical and we compute. And we'll go through and we'll get a solution here fairly quickly. And we did. And we should save that plan, sorry, and then exit and then go ahead and save our project. I won't spend a whole lot of time going through this data because it's very similar to what we've already seen, but let's just look at the profile. And you'll see 1.5, 6, 7, 8. We have our known water surface, and then it backs up here. It doesn't look exactly like the M1s that we've been drawing in class because it's a very mild water surface slope, and it'd be hard for me to draw this, so I usually exaggerate them on the board. But this is an M1 profile, and we could go in and find the flow depths at various locations along the channel as we did with the M2. So I'm going to exit this. We might just quickly look at the 3D plot, and you see it's actually almost looks like a steady or a constant flow depth, which it is quite close because 1.8 is very close to our normal depth of 1.75 meters. So really there's not much change in flow depth for this particular boundary condition. Okay, so go ahead and exit that. And that tells us how to change the boundary condition. So we changed the boundary condition at the downstream end, and we saw how that would impact our solution. Okay, the last thing I want to do is look at creating a more complicated geometry. So let's say we want to replace. There we go. All right, clean slate here. We want to replace our trapezoidal channel with a rectangular channel. We'll keep it very simple so I can do most of the math in my head. And we want a rectangular channel. Let's look at a plan view. So we're looking over the channel, plan view. And it's going to have the same bottom width. So let's say it's got a width of 8 meters, like so. But then it's going to narrow to a channel that has a width of 4 meters. And it has smooth linear segments connecting these two rectangular channels. So we have basically at this location, it looks like this, 8 meters. And we'll keep the same, let's keep the same depth, 2 meters. And then here, it's just narrower at 4 meters, right? Okay, same slope. We'll keep the bed slope as, bed slope is 0.001. Sorry, I'm still getting used to this pen. That means that every 100 meters, the change in elevation is 0.1. So some nice numbers that I can work with in my head. Okay, and then the only thing is we have to define the river station. So this is still going to be river station 0. The upstream end is still going to be river station 1400. And then let's make this a length of about 600. So let's say this is river station 600 and here river station 1000. So we have 400 meters of our channel contraction. Okay. Let's see how simple we can do this in HECRAS. Okay, because this is getting us closer to maybe more realistic geometry, because if we can do it for a rectangle, we could do it for a trapezoid, and we could maybe do it even for some natural channel geometry. Okay, so we need to go to our geometry editor. Let's go here. And I'm going to, again, as before, I'm going to get rid of all of those interpolated cross sections. So I'm going to go between two cross sections, and I'm going to delete the existing. And I'm going to go here and delete the existing. Get rid of all of those. Close. Now I need to modify. I'm going to go ahead and actually I'm going to delete this cross section too, the 100. Then I'm going to modify 0 and 1400, the cross section downstream and upstream, to rectangular. And then I'm going to copy and interpolate as we did before. Okay, so let's go to cross sections. Again, river station 100 came up first nicely. I want to get rid of this, so I'm going to edit options. I'm going to delete this cross section. So delete cross section and reach one river station 100. Yes. Okay. Do you want the reach lengths to be accounted for removing this cross section? Yes. That means it's going to make sure that river station 1400 is really 1400 meters. Okay, and we can confirm that it just updated it. And so if we go to 0, there's 0. Okay. Now to make this a rectangle, rectangular geometry is much easier to put in. Instead, we have no side slopes. This is going to be, in fact, what I'll do is I'll use station -2, -2 at an elevation of 2, -2, -2 at an elevation of 0, 2 at an elevation of 0, and then 2 at an elevation of 2. And ideally, I would have set this up in Excel to make sure it looks right. But since it's a rectangle, I can do it in my head. And if I apply the data, oops, and it says left, right bank station. Yeah, we need to update the stations, but so I'm going to say that's okay. Left bank station is going to be now -2. My right bank station is 2. And let's apply this data so it looks better. Okay. Manning's end remains the same. That's the only thing we have to do. And I'm going to quickly go up and come back so that I can see. Now I've got a nice rectangular channel. It has a width from -2 to 2. The reason I'm using negative numbers is 0 is going to be my channel center line. This will make it easier to align my channel. Okay, and there's my Manning's end. My bank stations are there. Everything looks good. It's funny, it keeps the solution even though obviously the solution is not valid for this new geometry. Okay, now we're going to go and do the same thing for our river station 100. Except now our 0 is going to become -4 to -4. I encourage you, if you're having trouble following me, take the channel geometry as given in the previous slide and see if you can make it work in Excel, and then go in and put these values in. Okay, and then the left bank station is -4, the right bank station is 4. The data, and I'm going to scroll down and come back, and you can see I have a rectangular channel of width 8, and the channel height is still Fine. And the elevations don't change. It's still shifted by 1.4 meters because our slope is the same. Okay, now I'm going to go down to the downstream river station and 0, and I'm going to copy it to that 600 where the end of the contracted section. So I'm going to go Options, Copy Current Cross Section, and I'm going to enter it at river station 600. Okay. I'm going to change my downstream reach length. It's now 600 meters from river station 600 to river station 0. Manning's end remains the same. Bank stations remain the same. Elevations need to increase by 0.6 because of the slope and a distance of 600 meters. So I'm going to go to that handy tool, Adjust Elevations, 0.06 positive, my data, and there you go. So we now go from 0 to 600, and I'm going to do the same thing from 1400. Now notice we need to adjust these downstream reach slopes, but I'm going to do that last because I know I've got to copy another cross section in here, and that's this cross section at river station 1000. So I'm going to copy the current cross section to river station 1000. I'm going to say OK. And now the distance, the next river station downstream is 600. So I need to change this to 400. I'll pick this number quite nicely, right? Okay, there we go. And apply data. But I also need to shift the elevation down because we've now shifted 0.4 meters lower. And so we need to adjust the elevations. And in this case, it's our first negative. We want to lower the channel. And we do that, and there we are, and we apply our data. And our bank stations remain the same. We are good to go. All right. Okay, so let's check our, sorry, I did mention this, and then I didn't do it. We need to change here. This is also going to be 400, our downstream reach lengths from river station 1400 to river station 1000. So I change those and then apply the data. And we should be good to go. Let's check our profile plot. And it looks fine. There's, again, so we've now established a cross-section at our downstream end, at river station 600, at river station 1000, and river station 1400. And here's our contracted zone here. So this is where that 3D plot is really helpful. We can see if we can actually see that contracted zone. So I'm going to close that. I'm going to exit the cross-section editor. And now notice, it looks really nice, right? We've got our, it looks like it may have not updated our cross-section, our downstream length here. So I'm going to just double check that it is in there correct. And it is correct. It's just not updated on the figure. Okay, so I'm going to exit this. And I would like to save this geometry. So I'm going to save geometry as, and let's call this geometry 3. Okay. There's geometry 3, and I saved it, and I'm going to exit the editor. And I'm going to look at the 3D plot to see if it looks like what I hope it looks like. And it looks not so bad, right? We see the wider cross sections. Oops. Sometimes this, as you know, if you played around with it for some of the others, you noticed it gets a little weird. But it looks like our proportions are all right, and you can see our contracted section there. Okay, so I'm pretty happy with this. I'm going to go in now and interpolate cross sections. So I'm going to reopen the geometry editor and interpolate cross sections between 1400, 1000, 600, and 0. So tools, cross section, interpolation between two cross sections. And let's start at, let's go ahead and start at river station 1400 and to 1000. And we can use a constant distance. Again, this one, we don't know how much things are going to change. We could do 100 as before. Just to do something different, I'm going to do a constant distance of 50. So I'm going to go ahead and interpolate this. And so we've interpolated 7 cross sections between 1000 and 1400 meters at a cross section spacing of 50. Okay. We can now do, and notice these have the bank stations all align. So it's really hard to see this, actually much harder than the trapezoid because of the cross-sectional, or the cross-sectional geometry is rectangular. Now I'm going to go to 600 and interpolate between 600 and 0. And you'll see it looks the same even though the channel is actually half as wide. And I'm going to do a constant distance again. And why not? I'll use 50 meters again. And so now it interpolates 11 cross sections between 0 and 60 at 50-meter distance. Okay, that looks good. Now, how do we handle that contracted zone between 1,000 and 600? Since it's a linear change in width, as we see here, right? Here's our wide section contracted to our small. This is where the cross-section interpolation tool is so useful. It will interpolate along the red and green lines linearly for us. And so I can still use a constant distance. And I'll go ahead and use 50. We might as well use the same for all of them. And I'm going to interpolate new cross sections. And there you go. Looks pretty good. I like this. I'm going to close it. And now look, we now have 0 to 50 to 100 at 150, 50-meter sections all the way across the channel. That's exactly what we want to see. I'm going to save this geometry and then exit the editor. And now I'm going to look at it in 3D, make sure it looks like what I would like it to look like. And it's a little bit hard to see from this view. Let's see if we can find a better view. Kind of get a top view of the channel. And you can see this starting at about 1,000, this smooth linear contraction from 1,000 to 600, and then constant from 600 to 0, and constant from 1,000 to 1,400. So we've created that smooth contraction here by only creating two cross sections, copying them, adjusting elevations and downstream reach lengths, and then interpolating new cross sections. So we are now ready to run a solution. And as we saw before, again, I wasn't going to do a solution, but I'm going to go ahead and do one to show you this really modular nature of this of HEC-RAS. So let's go ahead and we can set up a steady flow, and we can use our new geometry. Oh, we need to create a new plan. Sorry, new plan, and we can call this plan 5. Okay, and P5 for short. Our plan description is our rectangular contraction geometry. Let's go ahead and run just with run that 130 cubic meters per second. Keep it kind of simple on the flow side. We want to go back to actually that first flow we created. And remember, we have critical depth at the downstream end and subcritical, and we can save the plan, and we can go ahead and compute. And we get our simulation. Everything looks nice. We can close, save our plan just in case, and then exit. And now we have our solution here we can look at. And so we can look at our profile, and we can see here we have our nice M2. Notice it's a little bit clunky here. I probably should have refined this, and we could go back and do that if we'd like, but I'm not going to do it here. You can do that. That might be good practice for you on your own time. You can see the M2, and then notice between 600 and 1,000, we have another adjustment in the water surface due to that contraction, and then our 1,400 there. So there's our nice water surface profile. We could look at individual cross sections if you would like. Again, we could go to river station 0. And I took the option. Let's go back to variables. A while back, we unclicked critical depth. HEC-RAS keeps track of when you remove variables, so we've got to go back and add it in. And you see we've got critical depth here in our rectangular channel. We can scroll up and see how it's changing. Where it gets interesting, let's go to 600. And then we can notice the width here is 4. And we can see the width starting to expand as we move towards 1,000, where we reach 8 meters width. And then we can, scroll to our final upstream boundary. Okay, very nice, very nice. Exit that. Last thing we want to look at is the 3D plot. Again, these can be a little bit funky to play around. Oh, and I mean, this shows I wasn't really thinking ahead. You notice it's all above the bank stations because I didn't really consider how this change in flow, sorry, this change in geometry would impact the flow. So clearly 30 cubic meters per second, a channel depth of 2 meters is not sufficient. So I would go back and refine this. I'm not going to do that here because well, it's not necessary. We did what was the difficult part was getting the geometry in. We might be interested in these flow depths though here, so that we would know what how deep to make this channel, and we could do that, for example, with our detail table. So we can go to the upstream river station, and we can see our water surface elevation is 4.84. Our maximum channel depth is 3.43. So we're about 1.44 meters above that 2 meter channel that I made. And notice, again, we get that same error we saw when we ran the 60 cubic meters per second through our trapezoidal channel. So we could go back and fix that if we'd like, but I'm okay with it as a demonstration for how to put a nice, more complex geometry into HECRAS and how to solve it. So I'm going to go ahead and save project. And with these tools, now what we did today in this tutorial, we analyzed multiple discharges. We changed the boundary condition from critical to a known water surface elevation. And then we dealt with more complex geometry, and we saw how those tools in HECRAS allow us to, with a little bit of planning ahead of time, allow us to very quickly develop a more complex geometry. And then the modular tools let us insert that geometry very quickly into one of our previous flow plans and then run it. Okay, and that's it. So you've got some good tools now to work with HECRAS. If you would like more practice you can always go to the help file and work through the user's guide. Has a nice chapter that works you through an example problem, and then the application guide is nothing but examples, and all the data is provided here to help you get started. And you'll find this very relatively simple program to use once you get comfortable with it, and can be loads of fun. So enjoy your future HECRAS modeling.